Hello, and welcome to today's session on simple effects and factorial design hypotheses. Before we get started, as always, please make sure that you have the PowerPoint lecture notes printed in front of you so that you can take notes along the way. Today we'll be talking about these two ideas, simple effects and hypotheses for factorial designs. And just to set the stage a little bit and give you some context for today's conversation, please recall that we've been discussing complex designs, and a synonym for a complex design is a factorial design. In a complex or factorial design, we have more than one independent variable, and that raises some important questions about how we go to analyze our data. We might be looking at main effects at one particular point, we might be looking at interaction effects, and then today we'll also be looking at simple effects. In a prior video, we mentioned how to analyze main effects and interaction effects. Today we're going to be jumping in at the point where we've actually taken a look and we found that there's an interaction, and now we want to analyze these so-called simple effects. So let's get right into it, and just remind us that we can say that once we've found a significant interaction in a complex design, we must locate the source of the interaction using something called simple effects. That's a new concept for today. Let's see if we can define a simple effect. We might say that a simple effect is the effect of one IV at one level of the second IV. So just for absolute clarity, in a complex design, we have more than one independent variable. If you take a subsequent course in psychology and psychological statistics, you might get to something that's called a multivariate test. And in a multivariate test, we have more than one dependent variable. But today we're talking about complex designs that have multiple independent variables, but still only one dependent variable. And again, the simple effect is the effect of one IV at one level of the second IV. So this is a way of simplifying the very complex nature of our analysis, reducing the dimensionality, almost throwing away or disregarding one variable at a time. Okay? So sometimes these simple effects go by a different name. You might see in some journal articles, and even in some textbooks, that simple effects are occasionally called simple main effects. I point this out just so that you won't be confused if you do come across both of those terms. And I also wanted to make sure that we do understand that simple effects mean the same thing as simple main effects. And those two phrases are distinct from the earlier idea called the main effect. So there appears to be some overlap in those in that terminology, but there actually is a distinction to be made. Main effects are one idea. Simple effects, also called simple main effects, are a different idea from the main effects. Okay, let's see if we can look at one generic example, and then we'll see if we can get a little bit more specific to understand this idea of simple effects. One example that's generic would be the following. The simple effect of factor A at level B1. So that's one level of factor B. Later on, we could look at the simple effect of factor A at level B2. But we're analyzing essentially just one level of factor B at a time, and in this case we're looking at the influence of factor A at that specified level of factor B. Okay, so let's see if we can get into now a specific example that might make those A's and B's a little bit more tangible, a little bit more easily understood. Some of you might remember when we talked in Intro to Psychology about issues relating to depression. A very interesting phenomena is that some folks who are suffering from depression have a skew in their capacity to judge what kinds of things are in their control and what kinds of things are outside of their control. And we might think about this variable as a locus of control variable, and Julian Roeder in the 1960s developed a very famous scale called Roeder's scale for locus of control. And you might ask somebody to think about a scenario and report the extent to which they believe that scenario unfolded as it did because of external factors versus internal factors. And we can make that a continuous scale, and we can say that we can have relatively high external ratings or relatively low external ratings. And that's going to be the dependent variable in this table. And we'll be talking about that variable of external versus internal locus of control in the context of two other variables. One relates to depressed patients, and we're going to have three levels of that independent variable: folks who are not depressed, folks who are slightly depressed, and folks who are mildly depressed. So one of our independent variables is going to be level of depression. And we're also going to look at two different levels of accident. The type of accident can be either severe or non-severe. So we have some categorical variables here, and we're asking folks to report on this: the mean percentage of responsibility attributed to uncontrollable circumstances. That's going to be our dependent variable. Okay, so with that as a background, what we might ask you is something along these lines. You might say, would someone please describe the dimensionality of this experiment? Okay. And when we're asking for dimensionality, we're asking for a statement about the number of levels in each of our independent variables. And if it helps to give you an analogy, you might know that if you're building a house and you've got some lumber, you might be working with, for example, some 2x4s. When we're talking about a 2x4, we're saying that something might be 2 inches this way and 4 inches that way, and any number of inches along that dimension. But we're specifying how many inches in one dimension and how many inches in another dimension. Likewise, in experimental psychology, what we're doing is we're talking about the dimensionality of a study, and we're asking how many dimensions we have on this variable and how many dimensions we have on that variable. So in this particular case, the correct answer would be that we have a 3x2 because we have 3 levels of the depression variable and we have 2 levels of the accident variable. Equivalently, we can say that we have a 2x3 or a 3x2. We have no preference between those two possibilities. Okay, so now we have a 3x2 factorial design, and we're asking about the mean percentage of responsibility attributed to uncontrollable circumstances. Let's see if we have an interaction here. And if you'll recall from our earlier video, we have a couple different methods for discerning an interaction. Of most importance here is that we have a table filled with information, and usually when we have a table, the easier method for understanding whether we have an interaction or not is going to be the subtraction method. So let's see if we can walk through the subtraction method here, and we'll take a columnar approach to this because we have some columns for our depression variable, and we have just 2 numbers to difference in each of those columns. So let's see if we can walk through the subtraction method. I'll start here with the non-depressed level of the depression variable, and we'll take the difference between the mean percentage of responsibility attributed to uncontrollable circumstances, our dependent variable, in the severe condition versus the non-severe condition within the accident variable. So stated another way, all we're going to do is find the difference between these 2 numbers. And I'll use just the integer components of these for simplicity. So we're going to do 7 minus 30, and that's going to give us something like a negative 23. Okay? So negative 23 is our first difference from the subtraction method. Let's go on to the second level of our depression variable. These are the slightly depressed folks, and we'll do, again, 14, this time minus 16-ish. That will give us something like 2-ish. So we have minus 23 minus 2, 1 more, because we have 3 levels of this variable. So we'll do the mildly depressed difference score, and we get positive 16 minus 3-ish is going to give us something like positive 13-ish. So we have minus 23, minus 2, and positive 13 as our difference scores. And hopefully it's clear to you that we now have different differences. And that was our hallmark for establishing that we have an interaction in this table of data. Okay, there's another way that we can do this. A student very cleverly pointed this out a few years ago. If you can imagine the trend that we have on this level, the non-severe level of the depression variable, we're starting out at a very high score, we go to a much lower score, and a very, very low score. There's a downward trend going on there. By contrast, if you look at the severe level of the accident variable, across the same 3, we have a much flatter slope, and in fact, if anything, there's a slight uptick. We go from 7 to 14 to 16. So this line seems to be going upward, while this line is going very steeply downward. So whether we had used the subtraction method, or whether we had attempted to graph these data and look for non-parallel lines, both of those items, or both of those procedures, excuse me, would converge onto the idea that we have a statistically significant interaction in this data set. Okay. So in the sessions to come, what you and I will do is we'll learn something about additional basic ratios and the computations that formally allow us to say with great precision whether we have a statistically significant interaction or not. For the moment, we'll use these shorthand kinds of techniques, these rules of thumb, for looking at a set of tables or maybe looking at a graph and discerning whether we have an interaction using the subtraction method or using an evaluation of the parallelism of the lines that the graph is forming. Okay, so in our 3x2 design, we'll now see if we can look at these simple effects. And simple effects would typically be what we analyze once we've established that we do have a statistically significant interaction. And from our table a moment ago, using the subtraction method, it looked like plausibly we would have a significant interaction. So here's the same table. Okay? And when there is a significant interaction, we typically look at the simple effects. So let's see if we can look at 3 of the 5 simple effects that we're going to have in this table. And what we're going to do is simply circle the pairwise combinations across the different levels of our depression variable. So there is a simple effect of accident, that's severe versus non-severe, at each level of depression. So we have 1, 2, 3 of those different levels. Okay, and that gives us 3 of the 5 simple effects that we might have in this 3x5 design. Okay, which of these simple effects do you believe would be statistically significant and why? We'll let you stop the video and see if you can come to a conclusion on that. Okay, welcome back. So we would actually need to run a t-test in some software package to make a formal claim about whether we have significant differences in each of these 3. But just by eyeballing it, what we might see is that we have a relatively strong mean difference here in the non-depressed condition, and we have much smaller difference here, so that's probably non-significant. This one has a good shot at being significant. This one is somewhat intermediate. We have a difference of 13. That might be statistically significant. It might not, but it would be close, at least seemingly, given that we have a relatively large mean difference. Okay? All right, now let's go on and see if we can learn about the remaining 2 of our 5 simple effects in this 3x5 design. So there is also a simple effect of depression, that's factor B, at each level of accident, which is factor A. So a moment ago we were taking vertical slices out of this table. It's now time to take horizontal slices out of this table. The first horizontal slice is going to be the severe type of accident, and we can look for differences in the means across the non-depressed, slightly depressed, and mildly depressed folks at this level only, momentarily disregarding the non-severe data. Subsequently, we can take this blue row, and we can look for differences again across these 3 levels of depression, only looking at the non-severe level, excluding the severe level for the moment. Okay, so that's the remaining 2 of our 5 types of simple effects. Which of these simple effects do you suspect would be statistically significant and why? We'll let you stop the video and see if you can respond to that question. Okay, since there are 3 depression levels at each accident type, there's non-depressed, slightly depressed, and mildly depressed, even within, for example, the severe type, we would have to run some kind of an ANOVA, and then subsequently we'd have to run some post hoc tests to figure out which particular pairwise difference might be different from the next. Maybe there's going to be more than one difference, maybe there will be only one, if in fact the omnibus ANOVA turns out to be significant. Remember too that in addition to having these post hoc tests, such as the Chaffee or the Tukey or the Dunnett, or even the Bonferroni had this been a within subject design, that helps us to control for cumulative type 1 error, in addition to helping us pinpoint where the differences might be. Okay? So this might turn out to be a little bit more complicated because we might run a one-way ANOVA here, and then do the subsequent post hoc tests. And then after that, we might run a one-way ANOVA down here because we now have 3 levels of our independent variable. Okay, so let's consider this big picture. We've taken an example of a simple 3x2 where we had 5 simple effects. We sliced that table first vertically to get 3 of the 5 simple effects, and then we came back and sliced it horizontally to get the remaining 2 simple effects. In general, what we can say is that when we're beginning to analyze data in a complex design, it always helps to have an analysis plan, and the analysis plan that we're going to be following is the one that we show here. The first question that we will ask ourselves is about the A by B interaction. And please remember that we got into this kind of a design because we were really interested in trying to understand how variables are interacting with each other. That is to say that the real world contains many, many variables that are going to be influencing the behaviors, thoughts, and feelings that you and I are interested in investigating. And if we run only one variable at a time, we might have trouble generalizing back out to the real world. By using a factorial design, which is to say a complex design, we get some clue about how the variables might be interacting with one another. Now, once we have that interaction, though, it does raise some interpretive complexity. So usually our analysis is to begin with the interaction and to ask whether it's significant or not. And we're going to flow through this decision tree first based on whether that interaction is significant, we'll go over here, or not significant, that will bring us over here. Let's say we have the relatively simple case where we have a non-significant interaction. That would bring us to this point in the decision tree, and then our next question would be, are the main effects of A and B significant? So we could ask, is there a main effect of factor A? Separately, is there a main effect of factor B? And then if there are main effects there, we might go down one more level and say we need post hoc tests to tell us exactly where the levels of factor A are differing from each other. Separately, we need post hoc tests to tell us exactly where the levels of factor B are differing from each other. On the other hand, if we have non-significant interactions and we have no significant main effects, then we're done. We can stop with our analysis right there. Okay? All right, let's now go over and see what we would do had it been the case that we did in fact have a significant interaction. Remember, at this point, we usually prefer not to analyze main effects when we do have a significant interaction, because the interaction really clouds the interpretation of a main effect. It might be that, yes, we do get a main effect for factor B, but only because one of the levels of factor B was really driving that difference. So what we prefer to do instead is go to the simple effects whenever we have a significant interaction. And once we look at the simple effects, we can ask, are there any statistically significant differences among the simple effects? And if the answer to that is yes, then we, one more time, would perform post hoc tests in order to try to pinpoint where those differences might be. On the other hand, we would stop if in fact we had no significant simple effects. Okay, and as a reminder, when we're talking about these post hoc tests, we would be using maybe the Chaffee, Tukey, or Dunne tests. If we have a between subject variable, we might use something like the Bonferroni if we have a within subject variable. Okay, so we'll let you pause for just a moment. You can stop the video and jot down to this point what has been clear about what we've discussed. Okay, to begin to connect some of these ideas to what we've talked about before and to build on them, we'll take 3 potential pop quiz questions now. The first one is one that we've seen before, but it's important enough to remind us. So that question is, what is the simplest possible complex design? Okay. Second, we'll ask you this question. In your own words, explain what is meant by the phrase natural groups design. And then third, and maybe the most complicated of the pop quiz questions today, in your own words, explain how researchers could use complex designs to test a theory of why natural groups differ. Okay. We'll let you stop the video and respond to those 3 questions. Okay, welcome back. I will provide some answers for you today on these 3 questions. Hopefully you recall the answer from this one, which we saw in a prior video. What is the simplest possible complex design? The answer to that is a 2x2 design. And the reason that's the simplest is that a complex design, by definition, has to have at least 2 independent variables. An independent variable can have no fewer than 2 levels. So if we go with the simplest possible independent variable and the simplest or smallest number of such variables for a complex design, we'd wind up with a 2x2. The next question was, in your own words, explain what is meant by the phrase natural groups design. And here we can talk about natural groups designs as ones that are investigating groups that have pre-existing conditions. That is, we're defining the groups based on some criteria that you and I didn't assign to the participants. They had these criteria or these characteristics before coming into our study. Frequently, these are demographic variables. It might be something like age. We can have an older group versus a younger group. You didn't make your participants younger or older. They came to your study that way. It might be gender. It might be where they're from geographically. It might be their level of education. It might be their level of socioeconomic status. It might be any number of variables, their political orientation, a health condition, lots of different pre-existing conditions that we might have that define the natural groups. And frequently, psychologists are interested in those natural group variables. It would be a type of independent group design. Okay, let's go on to this last question. In your own words, explain how researchers could use complex designs to test a theory of why natural groups differ. Okay? This one actually requires a bit of explanation. So what we're going to do is break out of this presentation, and I've got something for us on the board. Okay, so what we'll do here is try to understand why it is that we can use factorial designs to determine why natural groups differ. Or I should say, how it is that we can use these designs to come to those kinds of conclusions. Really powerful. I think this is one of the more subtle points in the entire semester. I also think it's one of the most important points of the entire semester. So again, for clarity, using factorial designs to determine why natural groups differ from each other. Okay? And it's very interesting that natural groups differ on any number of dependent variables. We might begin to ask, why is that the case? So some authors have suggested a 3-step process for doing this, trying to understand why natural groups differ from each other. The first bit is to develop a theory about why it is that these natural groups are differing. And remember that your theory has to be testable. So we have some pre-existing groups, they're differing on some dependent variable, and we might ask, why is that the case? We'll develop a testable theory. The second step is to identify a variable that is manipulable. That is, we're going to manipulate a second independent variable to tell us something about our first independent variable, which was our natural groups. And hopefully that will be a variable that is not only manipulable, but directly relevant to our theory about why it is that these groups are differing from each other. And then finally, we're going to test the interaction between those two independent variables, one that we are manipulating and that flows directly from our theory, and the other variable, of course, is the natural groups variable itself. Okay, so again, those steps are develop a theory, identify a variable to manipulate, and then test the interaction between that manipulated variable and the natural groups variable. So you can see that the interactions are playing a very, very big role, and this is the first point in the semester where we can really do something like this simply by the research design. Right? And so we needed to get all the way up to factorial designs before we could begin to answer or to address questions like this. So let's see now if we can take this abstract set of steps for investigating natural group differences and see if we can get to a really concrete example. Okay, so as you might remember, in Intro to Psych you learned a little bit about chunking. Chunking was a phenomena that we described in the topic of memory, and you might remember that we can recall typically more items if we have some way of organizing the information into so-called chunks or groups of information that we can subsequently recall. Okay, so that idea of chunking is going to come back when we look at how a particular pair of natural groups will differ from each other. Some people have noticed that musicians are better than non-musicians at recalling melodies. Now maybe that surprises you and maybe that doesn't. You might say, well, of course musicians would be better than non-musicians at recalling melodies. But it wouldn't have to be that way. More importantly, it's not entirely clear why it is that musicians are better than non-musicians at recalling melodies. So let's see if we can develop a couple of different theories, and then we'll walk through one of those theories using these three steps. One possibility is that musical training just tends to enhance memory in general. And so if that's the case, then we would expect musicians to be better than non-musicians at recalling melodies, but also at recalling numbers, or recalling pictures, recalling anything. Because according to that theory, it would be the case that musical training just enhances memory overall. There's a different take on this. Maybe a second theory could be something like, well, maybe people who happen to have better memories, for whatever reason, are drawn to musical training. So you can imagine that we might have a bell-shaped distribution of memory ability, and according to this theory, it might be the case that folks who are at the higher end of the memory ability distribution, for whatever reason, are drawn to musical training. So it's not that the training itself enhances memory, it's just that we have a bit of a selection bias. Another interesting theory, and that would explain, perhaps, why it is the case that musicians do better than non-musicians when recalling melodies, for example. Okay, there's yet another theory, and that relates to our earlier idea of chunking. Remember that when we chunk, we're organizing the information into manageable units, and then we're recalling the entire unit or the entire chunk. So it might be the case that when musicians are being trained, they learn something about how melodies work, and they learn rules about melody through courses in music theory, for example. And because they've learned these rules, they're able to identify patterns in melodies, and they can chunk them really quite effectively, and then simply recall the chunks. Now what's interesting about this theory is that it doesn't suggest that the musicians have better memory in general. It says that the musicians have better memory in a very domain-specific manner. That is to say that they can use their music theory knowledge to chunk, but they probably couldn't use their music theory knowledge to chunk something that doesn't follow music theory. So what the researchers might do here is then develop a theory about why these groups differ, and according to the theory that we're developing now, this third theory, we might say that the musicians do better than the non-musicians at recalling melodies because they can chunk according to music theory. Okay? All right, so then we can say we want to identify a manipulable variable, and what we might manipulate is whether a melody to be recalled actually has good structure according to music theory or poor structure according to music theory. So we would have a good and poor structure variable, and this would be describing the kind of melody. The melody is either very consistent with what we learn about in music theory, or it's very inconsistent with that. If it is consistent, then we can chunk and we can take advantage of that. The other variable, of course, is musicians versus non-musicians, and we might find a pattern of data that would reveal an interaction. So let's walk through the interaction and fully understand this graph. On our y-axis, as always, we're plotting our dependent variable, and this might be the extent to which we can recall or remember the melody that had been presented. And some of those melodies have good music theory structure, others have poor music theory structure. On our x-axis, we're plotting musicians versus non-musicians, or the extent of training that they've had. And what you can see is that for the musicians, we get a huge difference between the recall level if the stimulus had a good structure versus a poor structure. So here, when we have a good musical structure, the musicians are recalling that very, very well. But if we manipulate the structure and now make it inconsistent with music theory, all of a sudden performance falls off for the musicians. Interestingly, if you look at the non-musicians do equally poorly in these two different kinds of stimulus conditions. They do equally poorly whether we have strong or not so strong melodic structure. So it looks like the only reasons why the musicians are going to be performing better than the non-musicians is that they can exploit a particular feature of the stimulus, maybe the extent to which that stimulus adheres to musical theory. So what we've done then is we found an interaction. Hopefully you can see that if you connect like terms, this one to that one, we get a downward slope. If we connect like terms, this one to that one, we get a flat slope. We have very diverging lines, so we have non-parallel lines and strong evidence for an interaction. This interaction itself constitutes evidence in favor of our theory. We always want to be careful. We don't say that we've proven our theory, but we do have information that's confirming the theory. Also of interest here is we have some information that's disconfirming to other theories. Remember that we said it might be the case that people who are musicians happen to have had a pre-existing better memory. Had that been the case, this data set would have been up here rather than down here. So it's not that musicians have a pre-existing better memory, nor is it the case that music training generally improves memory, because had that been the case, this would be up here and not down here. Clearly, the musicians are exploiting something that pertains to their training in music theory, and that explains this kind of a difference. So a very interesting way to investigate why it is that natural groups differ, and to wrap that up, again, the 3 steps were develop a theory about why those groups differ, then see if you can identify a manipulable variable that relates to your theory, and then test for the interaction. To the extent that you have a significant interaction, you have evidence at least consistent with your theory. If you don't wind up with a significant interaction, then you have a disconfirmation of your theory. Okay, we'll let you stop the camera and jot down what is confusing about this, and also, importantly, what is clear about this. That's critical for your metacognition. Meanwhile, I'll set up the next slide. Okay, welcome back. Now we'll proceed to talk a little bit about the different kinds of hypotheses that you can have for a factorial design. Remember that in the one-way ANOVAs, the hypotheses were relatively straightforward because we had only one independent variable. Now we have many independent variables, so this raises some issues about what the hypotheses might look like. The good news is there is some carryover from what we learned before. As always, these factorial ANOVAs that we might run, these factorial designs, are always going to be about comparisons of the mean. They're always going to be about issues relating to the sample from, or drawing an inference about the population from the sample. So we are engaging in inferential statistics here, and for that reason, we're really hoping to learn something about the population. So we continue to start out with our favorite prepositional phrase, in the population, and we might go on to say something like this: the means will be the same across all levels of factor A. So once again, we're calling for the equality of means. We might do the same thing for factor B. In the population, the means will be the same across all levels of factor B. Okay? And then we might have a interaction effect that we're trying to describe, and we might say that in the population, differences among the levels of factor A will be the same at each level of factor B. This particular statement follows very closely to our subtraction method. Remember that our subtraction method was a way of discerning whether we had an interaction maybe in a table of data, and we said that if we had different differences, we had evidence for an interaction. If we don't have different differences, but rather if our differences are the same as each other, then we have evidence against the interaction. And that's really what the null hypothesis would be stating for the interaction. So one more time, in the population, differences among the levels of factor A will be the same at each level of factor B. To the extent that's true, then we don't have an interaction. Okay? Now these are some generic statements because we're talking here just about factor A, factor B, and factor A by B. And that can be helpful to allow us to think very broadly about any kind of variable that you might be interested in investigating. But what we can say is that sometimes that's a little bit too abstract, so why don't we see if we can now get a little more concrete and offer a specific example. So here's now the same structure that we had in the previous slide, but we'll throw in some actual variables. So consider a study in which a story is presented and the story contains either 0, 1, 2, or 3 violations of physical laws. As an example, we can create a study that has a violation of gravity. Maybe gravity is suspended. Maybe the story contains something about time travel, or maybe it changes the way that that light operates or that sound operates. There are lots of different ways of violating physical laws. And we can have either 0, 1, 2, or 3 violations built into our story as one of our manipulable variables. Okay, participants rate the plausibility of the story, so that's going to be our dependent variable shown on our ordinate as we're manipulating the number of violations. And then we also want to know, as researchers, whether the plausibility ratings depend on the number of violations, but also a second factor, namely the participant's mania level, the extent to which the participant scores high, for example, on a inventory of mania. You'll remember that in earlier videos we've talked about having inventories for depression. We can have an inventory perhaps for mania as well. And we might have a high mania group and a low mania group as one of our independent variables. This would again be a between subjects variable, and it would be a natural groups variable. Okay, let's go on and take a look at some other kinds of hypotheses. In the population, the mean plausibility ratings will be equal across number of violations. So now we've taken what used to be factor A, we've swapped that out and swapped in the specific variable that we're interested in investigating. Let's now take a look at factor B. In the population, mean plausibility ratings will be equal across mania levels. It used to be factor B, now it's something specific, level of mania. And then here it is for our interaction. In the population, differences among the means for number of violations will be the same at each level of mania. So again, we're really asking the question about whether we have different differences or whether we have similar differences. Okay, so that was the case where we happen to have maybe a 4x2 design. We had 4 levels of one variable, and our second variable had 2 levels. Now we can increase the complexity of the design by going all the way up to 3 independent variables, and after that you could do 4 and 5 independent variables. You'll see this gets to be a little bit tricky, but just to whet your appetite for what can be accomplished by these complex designs, these factorial designs, we'll take a look at some of the hypotheses for a 3-way ANOVA. Let's see what we get. In the population, the interaction between factor A and factor B will be the same at each level of factor C. Okay, so now we have 3 factors, A, B, and C, and we're looking at the A by B interaction at the first level of factor C. We'll hold on to that just for a moment, and then we'll look at the A-B interaction at the second level of factor C. Okay, let's see if we can now slide in some of our variables. In the population, the interaction between number of violations and mania will be the same at each level of gender. Okay, so we can look at the A by B interaction for men. We'll hang on to that. We'll look at the A by B interaction for women. And to the extent that those are the same as each other, then we have no evidence for a 3-way interaction. But if we're getting very different interactions at the male level of our gender variable than we are at the female level of our gender variable, then we have evidence for a 3-way interaction. Okay, so that was a lot. We've talked about simple effects in complex designs. We talked a little bit about how we might be able to take advantage of take advantage of complex designs to understand how it is that natural groups are differing from each other. And we developed a 3-step process for that. And then we went on to understand how these hypotheses might be written for the main effects as well as for the interaction effects, whether we have a 2-way design or even a 3-way design. So why don't you make a note of what has been very clear to you so far in this presentation, or throughout this presentation, and also, importantly, make a note of what remains unclear. I look forward to taking your questions in class. See you in class.